Derivation of the identity \sin 2a plus \cos 2a equals 1. Welcome, everyone. In this subsection, we are going to walk through the step-by-step derivation of one of the most fundamental identities in all of trigonometry. Now, before we dive into the math, let's clarify what we mean when we say trigonometric identity. An identity is simply an equation that remains true for every possible valid value of the angle we are using. Today, we are focusing on a very special one: sine squared of a plus cosine squared of a equals 1. You might have heard this referred to as the Pythagorean identity. As we will see in the next few slides, this isn't just a random rule. It is a direct consequence of the Pythagorean theorem that you likely already know from studying right-angled triangles. Prerequisites. Now, before we jump straight into the derivation we saw introduced on the previous slide, we need to make sure we have our foundations solid. To understand where this identity comes from, we need to recall two essential mathematical concepts. First, let's look at the Pythagorean theorem. You might remember this from your geometry lessons. In any right-angled triangle, the square of the hypotenuse, which is the longest side, located directly opposite the right angle, is exactly equal to the sum of the squares of the other two sides. To put this into a mathematical formula, let's imagine a triangle, ABC, where the right angle is located at vertex B in this case. The theorem tells us that AB squared plus BC squared equals AC squared. Second, we need to refresh our memory on the basic trigonometric ratios. We will be using these ratios to transform our side lengths into sine and cosine. For an angle A within our right-angled triangle ABC, remember that sine of A is defined as the ratio of the opposite side to the hypotenuse, which in our triangle is BC divided by AC. Similarly, cosine of A is the ratio of the adjacent side to the hypotenuse, which is AB divided by AC. Keep these two definitions in mind, because in the next slide, we are going to use them to perform the actual algebraic transformation that leads us to our identity. Step-by-step derivation. Now that we have refreshed our memory on the Pythagorean theorem and the basic definitions of sine and cosine, let's move into the actual derivation. On this slide, we are going to walk through a logical sequence of algebraic transformations to see how those side lengths actually turn into the identity we are looking for. First, let's look at step 1. We will start with the foundation, the Pythagorean theorem. Imagine a right-angled triangle, ABC, where the right angle is located at vertex B based on what we just reviewed in the previous slide. The theorem tells us that the square of side AB plus the square of side BC is equal to the square of the hypotenuse, AC. In notation, that is AB squared plus BC squared equals AC squared. Next, in step 2, we need a way to introduce those trigonometric ratios we mentioned earlier. To do this, we are going to divide every single term on both sides of our equation by the square of the hypotenuse, which is AC squared. When we perform this division, we get AB squared over AC squared plus BC squared over AC squared, which equals AC squared over AC squared. Finally, in step 3, we simplify these expressions to make them look more manageable. We can rewrite those fractions as the squares of individual ratios. So, the fraction AB over AC squared becomes the quantity AB over AC, all squared. Similarly, BC over AC squared becomes the quantity BC over AC, all squared. And, as you can see, any value divided by itself is simply 1. This leaves us with the quantity AB over AC squared plus the quantity BC over AC squared equals 1. In the next slide, we will take this one step further by substituting our sine and cosine definitions into these ratios to reach our final identity. Step-by-step derivation continued. Step 4. Substitute the trigonometric ratios. If you recall from our prerequisite slide, we established that the ratio of the adjacent side to the hypotenuse, which is AB over AC, is equal to cosine of A similarly. The ratio of the opposite side to the hypotenuse, or BC over AC, is equal to sine of A now. We simply substitute these ratios back into our equation from step 3. When we replace ob over AC with cosine of A and BC over AC with sine of A, our equation becomes cosine of A all squared plus sine of A all squared equals 1. Step 5, final notation. To make our work cleaner and more professional, we use standard trigonometric notation. In trigonometry, instead of writing the entire term in parentheses, we write the exponent directly on the function. So, rather than writing sine of A all squared, we write it as sine squared of A. Following this convention, our identity is expressed as cosine squared of A plus sine squared of A equals 1, or, as you will more commonly see it, sine squared of A plus cosine squared of A equals 1. It is important to note that for this specific derivation using a right-angled triangle, this identity is valid for all angles where the angle is between 0 and 90 degrees, inclusive. Now that we have successfully rewritten our fractions as squares of ratios in the previous step, we move into the final stages of our derivation. Now, let's look at how this fundamental identity actually applies to a real-world scenario involving a ladder. Real-world application example. Now that we have successfully derived the identity through algebraic steps, let's step away from the abstract equations and see how this actually works in a real-world scenario. Imagine you have a ladder leaning against a vertical wall. If you look at the setup, the ladder itself, the wall, and the ground form a perfect right-angled triangle, just like the one we used in our derivation. Let's consider a specific scenario. Suppose the length of this ladder is fixed, it doesn't change. Now, imagine you adjust the angle, which we will call angle A, at which the ladder touches the ground. As you tilt the ladder more upright or more flat, the height it reaches on the wall, which is our opposite side, and the distance from the base of the wall to the ladder, our adjacent side, will both change. Here is where we can apply the identity we just proved. Let's represent the fixed length of the ladder with the letter L using our basic trigonometric ratios from the previous slides. We can say that the height the ladder reaches on the wall is L times the sine of angle A. Similarly, the distance from the wall to the base of the ladder is L times the cosine of angle A. If we take these two values and apply the Pythagorean logic, we square the height, which gives us L squared times sine squared of angle A, and we add it to the square of the distance, which is L squared times cosine squared of the angle A. When we factor out the L squared, we are left with L squared multiplied by the quantity sine squared of angle A plus cosine squared of angle A. Now, remember the identity we derived in the previous slides. We know that sine squared of angle A plus cosine squared of angle A is exactly equal to 1. So, our equation simplifies beautifully to L squared multiplied by 1, which is simply L squared. This confirms that no matter how much you change the angle A, the relationship between the height and the base always remains consistent with the fixed length of the ladder, squared. It's a powerful way to see that the identity isn't just a rule on paper, but a fundamental truth of geometry. Common mistakes to avoid. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even when you understand the logic of the derivation we just walked through, it is very easy to fall into certain traps. First, let's talk about notation confusion. This is perhaps the most frequent error I see in student work. Please be very careful not to confuse sine squared of A with the sine of A squared. When you see sine squared of A, it simply means the sine of A, multiplied by the sine of A. However, if you write sine of A squared, you are actually calculating the sine of the angle A after it has been squared. These two expressions represent entirely different values, so always keep an eye on where that exponent is placed. Second, let's revisit the derivation process itself. During step 2 of our derivation, we divided every term by the square of the hypotenuse, which was a c squared. A common mistake is to divide by the base, or a b, or the perpendicular, or bc, instead. Remember, the goal of this algebraic transformation is to make the right side of our equation equal to 1. To achieve that, you must divide by the term that stands alone on the right side of the Pythagorean theorem, which is the square of the hypotenuse, a c squared. Finally, a quick reminder regarding the scope of this identity. Because our entire derivation is built upon the foundation of the Pythagorean theorem, this specific identity is strictly tied to the properties of right-angled triangles. Therefore, you should only apply these specific ratios and this identity when working within the context of right-angled triangles. Keep these points in mind as you practice, and you will avoid the most common errors. Key takeaways. All right, we have reached the end of our lesson, so let's take a moment to recap the most important points from today's derivation. First and foremost, remember the identity itself. Sine squared of a plus cosine squared of a equals 1. This is the fundamental relationship we've been working toward. Next, it is crucial to remember its origin. As we saw in our step-by-step derivation, this identity isn't just a random rule. It is derived directly from the Pythagorean theorem, where a b squared plus bc squared equals a c squared. The core logic behind the entire process was the algebraic transformation we performed in the middle of the lesson. By dividing the Pythagorean equation by the square of the hypotenuse, we were able to transform simple side lengths into the trigonometric ratios we use in trigonometry. Finally, keep in mind the validity of this identity. This relationship holds true for any angle A for which sine of A and cosine of A are defined. I hope this derivation has given you a clear understanding of where this identity comes from and how it functions. Great job following along today.